given by Cheng, the more natural composite Higgs models. So there are something not so natural, but the thing is the more natural ones.
Okay, thank you for the invitation to give a talk here. This is based on the work in progress. Okay. Okay, with a new student, Cheng, who is also from Taiwan, who is taking the qualifying exam now. Now we know we have standard model that electrical symmetry is broken by a scalar Higgs field with the vacuum expectation method. This is the potential we write down with two parameters, the quadratic term and the Quartic term. Now now we know the Higgs web, and now we also measure the Higgs boson mass. We can determine these two parameters. So the mass parameter is about negative 88 GeV square, and the Quartic coupling is about 0.13. Now, as well known, the standard model Higgs suffer from the hierarchy problem to receive the quadratic divergent radiated fractions from the interaction with standard model field. The biggest contribution coming from the top bulk loop, because the top Euclid coupling is the biggest coupling in the standard model. Now, the solution, the hierarchy problem has been driving the new physics beyond the standard model for a long time. The solution to the problem based on symmetry argument requires some new particles related to this standard model particle by some symmetry, such that they can cancel this loop contribution. Now, in particular, we need a top partner which is quite close to the weak scale in order to make this standard model natural. Now, however, in traditional models, these top partners also carry colors. If they are colored, then they can be copies produced at the LHC, and then they are being extensively searched for. And so far, we haven't found any top partner yet. For example, here these are the bonds on the scalar top partner, like in supersymmetric theories. Here's fermionic top partners. These are over for the composite Higgs type models. And now the bonds are already, for most of the cases, beyond 1 TeV, like in this case, getting to 1.3 to 1.4 TeV, depends on the branching fractions. So now if we have the cutoff at beyond 1 TeV, that's already introduced some tuning to the Higgs potential. For example, if we just calculate the top loop contribution and you cut it off at, for example, 1.5 TeV, you find its contribution to the quadratic term is negative 250 GeV square. It's already bigger than the 88 GeV square we talked about earlier. So one already needs some cancellation to achieve the potential. But if this is just a number, maybe the tuning is not so bad yet. One probably wouldn't lose too much sleep over this if this is just a number. But in actual models, usually the tuning is much worse. For example, in supersymmetric models, the contribution is usually enhanced by a log due to the rounding from high scale to the weak scale. Now, if you think the supersymmetric model is valid up to the very high scale, dot scale, or Planck scale, Now, in most composite Higgs models, in fact, when we calculate the Higgs potential, we find there are some even larger UV contribution to the Higgs potential than this one, which we will discuss later. So, in fact, that's cause additional tuning required in those type of models. Now, tuning can be reduced if the top partners do not carry standard model color. These are the so-called neutral naturalness models. And I have been working on these type of models, and also I gave talks before in the last year or before. So, but this is not, we will not talk about this type of model today. We will instead focus on the composite Higgs model. So let's just briefly remind you what the composite Higgs models are. Now, we have assumed that the Higgs is composite, but the strong dynamics should occur at a much higher scale. To naturally separate these two scales, we would like to usually think it's more natural to have a Higgs field arise from as a pseudo-Nambu-Goldstone boson of the spontaneously broken global symmetry of the strong dynamics from some global symmetry G broken down to H. Okay, this is analogous to the pions in QCD. Now, the most studied model is so-called minimal composite Higgs model. It's based on the posted like G is SO5 and it's broken down to H, which is SO4. This produces 4 Goldstone bosons. This is identified as the 4 component of the Higgs field. Now, the standard model gauge, electroweak gauge group SU2 cross U1 is embedded in SO5 cross U1. In order to accommodate the hypercharge, one is going to need an additional U1 gauge group to account for this for the U1 quantum number. Now, the SO5 breaking lip down to SO4 is the size is F. This is slightly misaligned with the direction which preserved the SU2 cross U1. So that it also breaks SU2 cross U1, but only due to this small misalignment. The small misalignment is identified as the Higgs level V. We assume this V is much smaller than the global symmetry breaking scale F. Now, another important ingredient for the composite Higgs model is the partial compositeness. Now, this is to generate the standard model Yukawa coupling. You want to couple the standard model fermion to this composite Higgs. Now, to do that, we assume that some elementary standard model elementary fermions mix with some composite operators of the strong dynamics. The strong dynamics also produce some composite operator which produce resonances. Among this resonance, there are some resonances have the same quantum number as the standard model fermions, so they can mix through these type of couplings. Now here in this operator, the little q's represent the elementary fermions, and O represent the composite operators. Now, the standard model coupling can be generated at this order. It's proportional to the coupling of both these partial compositeness coupling, and divided by some strong coupling of the resonances. The strong coupling of the resonance is just analogous to the G rho in QCD, and one typically expected to be much bigger than 1. And the resonance created by this composite operator will have a mass roughly corresponding to this strong coupling times the scale F. Okay, so from this one can define some epsilon number, which is just ratio of this partial compositeness coupling to this strong resonance coupling. G, one typically expect this number to be smaller than 1. So the Yukawa coupling is suppressed by this epsilon left times epsilon right, so that it can be, because of this suppression, then this Yukawa coupling can be integral smaller than 1 to produce the standard model Yukawa coupling. Now one has what are these top partners of the standard model which cut off the loop contribution. They are created by these composite operators. Now the resonance created by these composite operators are divided into representations of H, because G is broken. So these composite resonances, they only form representation of the unbroken group H. Now, however, one need all of them together to cut off the contribution to the Higgs potential. Together they play the role of the standard model fermion partners. Now, because adding just to contribution of any single set of representation G is not enough. One need the whole set to make it finite. This can be shown explicitly in those so-called holographic models or some disconstruction of that. For generic models, one usually just impose this condition finiteness of Higgs potential with the Weinberg sum rule. Now, as we said, because these standard model fermions don't form complete representation of G, so in fact these couplings break the global symmetry. Therefore, the Higgs potential is generated by these partial composite couplings. And also other like a standard model gauge couplings which also break the global symmetry. Now, with this we can generate a Higgs potential. The leading order Higgs potential takes this form because now Higgs is a non-Goldstone boson, so it's a periodic. Therefore, we write the potential like a sign, like sinusoidal functions. But for small h compared with f, then you can expand it as roughly this is the quadratic term, this is roughly the quartic term.
You mean f to the fourth?
Huh?
You mean f to the fourth?
No, that's was how it was defined in people. Yes. Both alpha and beta have dimension 2 in this dimension, in this writing. Okay. So alpha just behave like the Higgs mass square. Beta is like lambda times f squared. Okay. So then the alpha betas are model dependent. They are generated by these explicit breaking parameters. So alpha beta have the same dimension. Now to achieve the realistic electroweak symmetry rating with V much smaller than f, one can minimize the potential. One finds alpha divided beta equal to 2 which is 2 times sine squared h over f squared, roughly just 2b squared over f squared. So this means if you want this to be much smaller than 1, one need alpha to be smaller than beta. Okay. And also the overall size, the overall size of this coupling, one also need the right size to give you the right mass for the Higgs boson. However, in most composite Higgs models, one generally expects that the alpha to be bigger than beta rather than smaller than beta. So which this is the source of the tuning. Let's see some explicit examples. For example, just take the minimal composite Higgs model. Now if we assign, we choose the resonance, strong resonance to belong to the phi of SO5, then one can estimate the potential like alpha and beta. Now at the 2 insertion of this coupling, one just generate the term alpha only. So the alpha is proportional to lambda left square or lambda right square. At 4 insertions, one can generate the term beta. So beta is rise at the order lambda to the 4th. If we write everything in terms of G sine f, as we defined earlier using the epsilon, one finds alpha arise at the order epsilon squared, where beta arise at the order epsilon to the 4th. This shows this model in general, one expects beta to be much smaller than alpha rather than bigger than alpha. So in order to get a realistic model, one needs to tune this term, to suppress this term, to make it much smaller than the naively expected value. Another issue is also if we compare this quadratic contribution with the infrared contribution. Earlier we talked about the top loop contribution. Remember, top loop is proportional to top Yukawa coupling square. The top Yukawa coupling itself is epsilon left times epsilon right. So y squared is of order epsilon to the 4th power. This is already too big, right? Earlier we estimated this is 250 GeV squared. But then now the UV contribution is epsilon squared, so in fact it's even bigger. That's also another point of the tuning of the composite Higgs model. Now one can change some result by choosing different representations of this composite resonance. For example, if you choose them to be 14 representation of SO5, one can generate alpha and beta at the same order. However, they are at the same order as epsilon squared. So now one can say, since alpha and beta are comparable, one needs only a bit of tuning to make alpha smaller than beta. However, both of them are in some sense too big. Not only you still need to suppress alpha, if you don't suppress beta, you get a too heavy Higgs boson. So these are the issue of the for most of the composite Higgs, the tuning issue for the most of the composite Higgs model. So we can see that in order to get a more natural Higgs potential, there are two things we would like to do. First is to suppress the order lambda squared contribution to the quadratic term in the Higgs potential, which makes alpha small. Second is to generate some quartic potential without inducing some quadratic terms, so that we can get a beta which is bigger than alpha. Now, these two things basically cause for the collective symmetry rating of the little Higgs mechanism, which we will use to build more natural models, as we will see. So, but let's go back to see why do we have Higgs potential arise at order lambda squared. This is because the resonance created by these composite operators are actually split into representation of H only. So you are forming only representation of H. They are not completely a representation of G. So the coupling do not contain any accidental symmetry, bigger symmetry to preserve the Goldstone nature of the Higgs field. So in order to suppress this contribution, we are looking for models where any single these partial composite coupling will preserve a larger symmetry which protect the Goldstone nature of the Higgs. And Higgs potential can only arise by combining at least two or more such couplings, so that we can suppress the Higgs potential. So some example can be achieved. This can be achieved with some choices of cosets. For example, here we talk about consider the coset SU5 mod SO5 and SU6 mod SP6, which are used in those little Higgs models. Probably not surprising. These will provide promising candidates. The reason is that if we choose all these composite operator to be, say, a fundamental representation of this SU5 or SU6, then when you break down to SO5 and SP6, they are still 5. They don't split, actually. They remain degenerate. One may say that the SO5 fundamental representation is real, where this SU5 is complex. But remember, we need the additional U1x charge. So even with SO5, with charge on the U1x is still complex. So they remain intact. Basically, they don't split after the breaking of the global symmetry. Now, because of this, in fact, they accidentally preserve a larger symmetry to protect the Goldstone nature of the Higgs potential. More explicitly, one can see, now this is an example of SU6 mod SP6, but SU5 mod SO5 work very similar. Now SU6 is broken by an anti-symmetric wave down to SP6. The wave is proportional in this way, so minus I. We define this as a sigma 0. Now using CCWZ, one can usually write the Goldstone boson as a matrix to see which transform on one side as in G, the other side as H. So let's be specific. Let's define some index structure. Let's call I as an SU6 index and alpha as an SP6 index. So this is to see matrix carry one SU6 index and one SP6 index. And the difference, the sp6 index alpha can be raised or lowered by the sigma 0. Now, for later use, we also define A as SU2 index and A as some generators. Now we can gauge the SU2 cross U1 group like this way. They are subgroup of this SU6. And unlike the little Higgs model, we don't gauge two copies of SU2 cross U1, just only a diagonal copy. Now the Goldstone matrix takes this form. Now in this breaking, we got 14 Goldstone bosons. It contains 2 Higgs doublets, H1, that's 8 degrees of freedom. 1 complex singlet, S, sitting here, that's 2 degrees of freedom, and the real triplet plus a singlet. So that's 14 degrees of freedom. And many of them, like these, will get mass from the gauge loop. We don't care too much. These are the important fields we will care about. Now, for partial composites, we can consider some composite resonance, which is let's denote them as a capital Q. They are 6. They belong to the represent 6 or the sp6, and with the U1 charge 1,6. And under the decomposition of the SU2 cross U1, they contain 2 doublets. That 2 and the 2 bar are equivalent for SU2, and the 2 singlet. The 2 doublets have the same quantum number as the left-handed quark, and the 2 singlets have same quantum number as the right-handed up and down quarks. Now one can write down the partial composite coupling like in this way. Now remember, this combination is the O operator, because O is SU6 representation, so we carry a SU6 index alpha. I, so it can be written as this combination, like the Goldstone matrix times this Q, which we contract alpha index here. So now this is our partial composite coupling. This is just the spurion which represent the symmetry breaking, which this means this elementary doublet only just mix with the first doublet in this composite operators. Now one can see that this coupling actually preserves a larger SU6 symmetry represented by this alpha index. You may say, well, alpha represents sp6 index. But from this point of view, it doesn't know whether it's SU6 or sp6, right? It's contracted in this way. One can explicitly calculate this one loop diagram. One finds that the contribution is a constant, independent of those numbers. The reason is that in order to know that this alpha is a sp6, one actually need an insertion of sigma 0, which is not here. Now to generate the standard model coupling, so now we also need a right-handed partial composite coupling. It can be written in this way. Instead of coupling to 6, we couple it to 6 bar. 6 bar can be formed by the same quark here, but with a sigma 0 inserted to flip to lower the index and couple to the C star. This sigma 0 switch the first 3 entries with the second 3 entries. Now by combining lambda left and lambda right, we can write down the coupling like this, and which contains the standard module couplings. Now this with this sigma 0 insertion, now SU6 is explicitly broken, so we can generate the Higgs potential. Now, but at the order lambda L squared times lambda R squared, which is the same order as YT squared. This is nothing but the infrared contribution we talked about earlier. Okay, so this will suppress. So that means in this model, the Higgs quadratic term does not arise at lambda squared, but just the partial coupling squared order. Now this is the first atom. Then to make the model more natural, we also would like to generate some Quartic coupling, additional Quartic coupling without the quadratic term. Now this can be achieved by the little Higgs mechanism. Now this is usually presented in this way. We need these two terms look like this. This is the singlet, the complex singlet coupled with the Higgs like this. Each term, in fact, itself is just the singular mass term. Okay. Now in the first term, it will invariant under some symmetry like this. The Higgs goes to boson, the invariant shift symmetry cancelled by this shift. Now this term, if you square it, looks like it contains a quartic term, but it's not really there because you can shift it away by using the symmetry. Also similar, this term itself, also there's a different symmetry which you can remove the Higgs boson. But because these two symmetries are different, when you have both terms, these two symmetries are incompatible. So when one integrates out the singular field, one generates a real quartic term for the Higgs, but another quadratic term. So to do that, we can, using the fact that in fact that's composite operator 6 contains two doublets of the same quantum number. Earlier we mixed the elementary quark with the first doublet. We can write down another coupling which makes the elementary quark with the second doublet, but then in such a way that you rewrite this as a 6 bar, that you use sigma 0 to fit the first 3 entries and the second 3 entries. You put this doublet to the first entry, then again using another spurion which coupled your quark doublet to this to the resonance. Now because we have sigma 0 insertion here, now the SP6 is broken. One can generate a term. One of the required terms, as we said earlier, sorry, this is typo, this should be lambda prime, from this loop, order lambda L to the 4th power. Now this indeed contains one of the terms we required earlier for the collected quartic term. Now one comment is that this doublet and this doublet should be different, Q and Q prime. Because that if they are the same, one would generate a lower order term, which is a typo for the singular or quadratic term in Higgs, which we don't want. This is because if they are different, one can assign different Patrick symmetry. This term violates Patrick symmetry. If we have different quarks, then the Patrick symmetry can be preserved, which will remove this term. Okay. Now, this is just one term of this collected quartic term. The other term can be generated by a different set of quarks or leptons, which preserve the other. Okay, I think one thing I didn't mention is that the reason why Higgs is protected is because you see these two spurions. They preserve the SU4 symmetry of the last 4 entries. Okay, this guarantees the Higgs is the boson boson, but the singular is not, because singular sits on the first 2 components. Therefore, singular gets a mass. Now one can write down another set of terms which preserve the other SU4 symmetry of the entry 1, 2, 3, 6. It's protected again the other term. Now the quartic term now is generated at order lambda L squared times lambda L prime squared. Remember the quadratic term is generated at order lambda L squared times lambda R squared. So if we can choose lambda L prime to be bigger than lambda R, we can get a bigger quartic term than the quadratic term. So more realistic, some realistic numbers will be presented in our upcoming papers. But here I just talk about the ideas. Now one can see that by choosing a suitable coset and representation, one can largely make the Higgs potential more natural for composite Higgs models. Now, but there's something in general always true is that in those composite models, the Higgs coupling to gauge boson fermions are modified by the order of v squared over f squared. Now typically one imagine this, to make a model natural, one doesn't want the C to be too small. But on the other hand, now the constraint is already at the order 10% level. But if we have additional quartic term compared with quadratic term, it's more natural to have a smaller C. One can maybe suppress this correction more. However, for this particular model, SU6 model, SP6 model, it has 2 Higgs doublets. So in general, there also can be some correct Higgs coupling deviation due to the fact there are 2 Higgs doublet mixing. Now, in order to satisfy the current constraint, it probably should be close to the alignment limit or decoupling limit. Now, however, the drawback of this model is that in this way, to implement partial components in general, it will induce the correction to the Z coupling to the standard model fermion due to the mixing between doublet and singlet. Now, these are very accurately measured to the order of 10 to the minus 3. So, to get a large enough Quartic coupling and to satisfy this constraint, the corresponding resonance should be close to about 10 TeV, in fact. This means that one probably doesn't want to use the top partner to generate this Quartic coupling because we want to keep the top partner like below like 2 TeV. But we have all these other quarks, like the first 2 generation quarks and the leptons, which their partners can play the role to generate these Quartic couplings. Now, I use the SU6 model, SP6 model to as an example to illustrate. One can also consider the SU5 model, SO5 model. Now, the advantage of this model is that it does contain the cosodial symmetry to protect the Z to B bound vertex. In fact, it contains this charge 5-third top partner for people who knows about the story of this, but I won't go into detail. Now, the collected Quartic, the suppression of the quadratic is very similar to the other model. The collected Quartic term works somewhat differently because the 2 doublets in the file have different hypercharges, so one cannot mix with both of them. So this can be obtained by using the neutrino couplings or adding new elementary fermions. So it's slightly different. But the drawback of this model is that this Quartic coupling is achieved by a Higgs triplet, which coupled to the Higgs doublet. So in general, the Higgs triplet will get a web, which will violate the custodial SU2 symmetry, which will have a very strong constraint. And also, if we use the neutrino to generate the Quartic coupling, it will produce a very large Majorana mass for the neutrino if the triplet has a web. So that's another problem. Unless we can suppress the web by using some T-parity or some symmetry, this model may require some additional tuning to make the to triplet web small. Okay, I think I will just stop here and thank you for your attention.
Okay, so questions? Yeah.
So are you going to do collective breaking for the first 2 generations?
Well, remember the Yukawa coupling is lambda L times lambda R.
Right.
Here you get a collective Quartic coupling just using the lambda L. So in fact, one can make the first 2 generation Yukawa coupling small by just choosing small lambda R.
So you use lambda R.
But keep lambda L of order 1.
Okay. So that's how you check.
Yes.
Other questions? Or other questions for the previous 2 speakers? Also, maybe we have 2 minutes. In particular, do you have a question to Wei Yi? When can you finish the kind of rush? Yeah.
Yeah. So for the neutron anomaly, for the neutron lifetime anomaly, what's the prospect of confirming it or it's experimental?
As I said, it could produce, it's quite large. Underground, look for some parameter space to see whether you can see multiplier in the 2 GeV region. So as I showed.
But for the model, you mean for the model?
For the model.
I don't know, but I'm just thinking
the model
for the
will
experiment.
expect some dipole as I showed for the mixing of the neutron and the chi. Yeah, so you go through some certain TeV physics will induce the mixing.
But just experimentally, are we going to learn, soon that the anomaly is actually there or not?
I hope so. I cannot answer that question. Any comment?
Okay.
I have a question along this one too. Your chi is bionic, it carries baryon number.
You carry baryon number, correct. We can assume baryon number conservation at this level.
Okay. Does this affect any early universe cosmology, like the biogenesis and other things? It's pretty light too. It's more or less within the range where you can. Yeah, I worry about the early universe cosmology if this, you have additional iron.
In fact, this actually fit into the asymmetric dark matter, because the chi and chi bar may not be equal populated. So as long as the asymmetric dark matter satisfies the condition, it should be, you can tune the model to satisfy the cosmology. But I did not do the detailed study. But it is very, it actually inherits some property of that asymmetric dark matter scenario.
Well, okay, so other questions? Back to Xinjia. Any? Well, okay, so if not, let's thank all speakers for this session. Well, just a few announcements. Okay, tea break, coffee break is outside. In the morning, when you come in here, maybe you don't have fresh hot coffee. So the hot coffee arrive a little bit later, 9 o'clock or something. But then you still have to come in here tomorrow, 8:30, right? We have some tea. So outside is break for coffee. Now lunch, just after the last part in the morning session, then just keep out your lunch box outside and then find somewhere comfortable or go back to the NCTS on the 4th floor or 5th floor. Then you can do some discussion and having lunch. And then dinner. Tonight we have the reception. All are welcome, but the place will be on the 4th floor for NCTS because usually we have some other places. This place is too small. On the 4th floor has more space. And for the conference banquet tomorrow evening, speakers, parallel and plenary speakers are invited. So if you don't want it, if you want it, sign up outside. All right. Okay. So maybe now can have a break. I'll come back at 11:10.